This is a short video about section 3.4 in Stein's number 3 book about attacking RSA. In this section 3.4, there are various ways to attack RSA. In this video, we'll focus on 3.4.1. How can you factor n if you knew phi of n? Where again, phi is Euler's phi function. It counts the number of integers that are relatively prime to n that are less than or equal to n. So here's the idea. Remember the setup for RSA. You've got a number n that has exactly two prime factors. Ideally, n is very large, meaning that these two primes are very large, so that anybody could know n, but it's hard to factor that number with a computer. Even a computer would have trouble factoring that number. What if somehow you knew phi of n? If you know phi of n, then what we're going to talk about is it's very easy to recover these kind of secret primes p and q. So if you could get your hands on phi of n somehow, we're going to talk about how can you recover p and q. And here is the deal. How do you do that? Well, phi of n, we're going to take phi of this number. Remember the properties of phi. That is going to be phi of p times phi of q, since p and q are relatively prime to each other. And so remember, phi of p, how many numbers are relatively prime to p that are less than or equal to p? Well, there's p minus one of them. And the same story with q, since those are primes. And now what we're going to look at is what happens when you FOIL that out. When you FOIL that out, you get pq minus the quantity p plus q plus 1. And now what we're going to look at, we're going to rearrange this equation here. Now, what do I know? I know that pq, that's n. And what else do I know? I'm going to solve this for p plus q. If I solve this equation for p plus q, that looks like what? P plus q, if I add that term over, looks like I've got n plus 1, and then I need to move the phi of n to the other side as well. All right. And so now we're going to be pretty slick. If your goal is to recover what p and q are, I'm just going to build this quadratic polynomial whose roots are p and q. And if you FOIL that out, here's the polynomial that'll have p and q as solutions. So again, you can build that polynomial if you know what phi of n is, which is very interesting here. And so then you could just use the quadratic formula to figure out what are the roots p and q. So that's bad. So that's why, in general, what's the point so far? If you've got n is equal to p times q, you want to make sure n is so big that computing phi of n is not an easy task. In fact, you want it to be damn near impossible. Because this shows that if somebody could compute phi of n, then your n is not a very good, not a good n for RSA encryption. So let's just walk through this example that's Stein lays out for us here. I take this number n, which is this pretty big number, 3, 1, 6, blah, blah, blah. It's a product of two primes. Unfortunately, though, I don't think it's too hard for Sage even to just compute what phi of n is. So in other words, that number is not big enough to put into practice to make like a real encryption, RSA encryption scheme using that n. So phi of n is not too hard to get from a computer, I don't think. So then what are we supposed to do? Well, we are going to, instead of p plus q here, remember the whole point is p plus q, it depends on n and phi of n. Maybe I didn't belabor that enough earlier. So what is this? This polynomial I have is x squared minus n plus 1 minus phi n plus n, right? So this polynomial has roots p and q, but notice all I need to know about is n and phi of n. Maybe should have said that earlier. Okay, cool. So in our example here, there's our polynomial f. And it's exactly the formula I just used, and we'll plug in just what are the numbers that I know here. And so when you simplify all that stuff, you probably believe it. Look how big those numbers are. Why would we lie? And you see that factors this way. And Sage wouldn't have too much trouble trying to just find the roots of a polynomial that big even. And you could recover those two things too pretty easily. You could get... I guess you could factor those using the quadratic formula, is what the next part's trying to say. And that's where you get your numbers from. So n factors as, well, this number is one of your roots here, and we found the other root would be this one too, when you do the minus. So notice this is only quadratic formula plus or minus, right? So this will be from plus, and then you could bet this one's when you put a minus here and a minus here. Okay, so you could also implement this in Sage, and just for your convenience, it would be good to just make a function out of it that'll just do it. So we'll define this thing, and this function's name is crack_RSA, and the things you need to know to do that are n and phi of n. So essentially, right, we just said if you have n, if you have phi of n, you can crack the RSA system if you know those two things. So the next thing we're going to do is we're going to tell Sage that we're going to play in the polynomial ring. And so that'll allow us to, we'll define polynomials. And the polynomial we want is this f that we just looked at. And remember, it's x squared minus n plus 1 minus phi of n times x plus n there. And remember that polynomial we showed above has roots p and q. And what do I want to do? Sage has built-in commands for, here's a polynomial, find its roots, and it's right here. I want it to return the following list of roots. I want it to return b for b that's in f dot roots. So when you run crack RSA, and just with the n that we had earlier, and then you happen to know phi of n again, I think Sage can compute that pretty quickly, the output will look like a list that has two things in it, and one of them's p and one of them's q. So again, the moral of the story is you want to pick n so large that it's nearly impossible for anyone else besides you to figure out what phi of n is.